water of, let's say, 30 degrees, and explain how we talk about that experiment. But for now, I'm just going to start a little bit with the different phases of a substance. We start with kind of solid. That's an ice cube. When we in physics want to draw a solid, we like to think about the particles. So for any solid, you will kind of draw a three-dimensional lattice, just explaining that in a solid, the particles making up that substance is in fixed positions. Am I able to draw a three-dimensional? Let's see. Can I connect the dots? Close enough. So here are kind of the particles making up the substance. We just call it a particle. That could be one atomic particle, or it could be more than one atom making up that particle. This could be a H2O molecule, for instance. So in a solid, these particles are in fixed positions. Can they move? What type of motion do you have in a solid, Emily? Vibration. They can oscillate back and forth around equilibrium position, so they can actually move. They can kind of vibrate. So kind of draw some points indicating that they can actually vibrate. Because what type of motion do we have? So I'm gonna write that here. How we physicists describe motion, we have vibration. That's when particles tend to vibrate along about the equilibrium position. So vibration is one type of motion particles can have. I'm going to do rotation. Let's say we have a diatomic molecule can rotate about its center. That's one type of motion. And the last one, the simplest, with kind of the most difficult word, translation. Not in translating languages, but translation, it means that a particle basically just moving. That's what we call translational motion. Let me write that translational motion. And what does this vibration in this solid, that gives it kinetic energy? And kinetic energy, how can we measure kinetic energy in a substance? What is average kinetic energy per particle in a substance? Emily? Temperature, yeah. So how much these particles vibrate, how fast they vibrate, that determines the temperature of that substance. So in a solid, the molecules can vibrate. The strong forces between the particles, so they're not free to move. They are fixed in their positions. And then we have the liquid. If I want to draw a liquid, I want to have a container. This is just a container. And now the strong forces between the particles when they were in solid, they're not as strong anymore. The molecules are now able to move in respect to each other, it takes the shape of the container. So there's still relative strong forces between the particles. So some of these particles, they cannot escape. They're still connected to the other particles, but they're not as strong, so they actually are able to move. Different ways to move, different types of motion. And then we have the gas phase. If I don't put a lid on it, the gas will disappear. Now, the distance between the particles are much greater. That means weaker forces. So now the forces between the particles are weak because the distance separating them are much greater. And the particles have translational motion. It can have rotational motion if it's a 2-atom molecule or a 3-atom molecule. Some vibration, but mostly it's translational motion and rotational motion.
Folk besked att några borde ha bena som
Denna.
denna problemet, den är connect. Kanske brukar det den bordet. Så flyttar det till den bordet.
And maybe next time don't ruin the table.
What the heck?
All right. So, in gas, the free to move, mostly translational motion and rotational motion, but of course, some vibrational motion will be present. And then it's the wording of it. What do we call it when we go from a solid state to a liquid phase? What do we call it in physics and in everyday life? Melting. Sometimes we in physics choose difficult word. In this case, we choose the common word. And if we go from a liquid to gas, what do we call it in physics? Maybe not in real life.
Okay, evaporation.
Evaporation, yeah.
Evaporate, yeah. Oh, vaporation?
Oh yeah, vaporization.
Oh.
Because evaporating, that's something related to it, but evaporation, that can only happen to the particles near the surface at any temperature. Melting takes place at melting point. Vaporization takes place in boiling point. Right, vaporization here. But evaporating, that can take place at any temperature, but only to the near surface molecules. Of course, evaporation increases with temperature as well. Yeah.
Are we gonna work backwards? Are we gonna go?
Yeah.
Oh, okay.
And of course, we need to also go. What's wrong with those pens? We need to go backwards as well.
You can just throw them.
I kind of like to have them there to just to mess up with the other teacher.
Oh yeah, nice.
Emily.
Just throw them. Condensation.
Yeah, condensation.
from liquid to solid.
So this is condensation, and what if you go with melting is one way, and the other one is
Solidifying.
Or is it
Sublimation.
Sublimation is from gas to solid, isn't it?
yeah.
Yeah. Formatting. Freezing. Oh.
Freezing. I think we're just gonna use freezing. Yeah.
Solidifying.
Sublimation is when you go from a solid to a gas directly.
And that's like what? What is that? Like the frost or something like that? What's an example of that again?
Example of sublimation is when you have carbon dioxide, what we call known as tørris. That goes directly from solid to gas,
Yeah.
not through the liquid phase.
Why?
You said carbon mono. What did you say? In English?
Dry ice, yeah. Dry ice, yeah.
Tørris.
Yeah.
Okay.
So why didn't it go through liquid phase?
Because there is one point there where that's we can do it when we draw the diagrams in, I think it's in chapter 10.
Right.
We can gonna draw the diagrams that
Oh, and then
Yeah.
over the diagram,
It's just
it's
pink.
actually like a
yeah.
Where are the dotted lines? No, no.
Um so what's important to know that
Don't worry.
at melting temperature and at boiling point, melting and vaporization requires energy. So these are processes that requires energy. You have to add energy in order to melt ice. If you have ice at 0 degrees Celsius, it doesn't melt automatically. You have to provide energy for it to melt. But if you put an ice cube on this desk, the surroundings will provide the energy needed to melt it. But you do require energy to melt something or to vaporize something at melting temperature and at boiling point. But the process of condensation and freezing, they release energy to the surrounding when it's taking place. When you go from gas to a liquid, it releases energy. When you go into a steam and your face feels warm, that's because the steam hits your face and go from gas to liquid, and it releases energy, and your face is absorbing that energy and it feels hot. So that's why when going into a sauna, especially in the face, you can feel the heat. That's due to the gas condensating. So that's releases energy to the surrounding.
Also a question. What is chapter 7? What is that? Like, what is chapter 7?
Chapter 7 is we go through it's kind of a mixture of topics within thermodynamics.
Because when Anna first introduced this chapter to us, I think there was a presentation that she did not complete.
Yeah.
We weren't able to do that. So what do we do about that stuff?
No, I think I am covering it.
Okay, perfect.
Yeah, I'm covering what's in the book.
That-
Yes.
Okay, perfect.
So this is the different phases of a substance, and we remember that when we have the concept of internal energy, I don't know if Anna especially talked about that, but internal energy, we talk about the energy of an ice cube or energy of the water. We have this thing called temperature, and that is the internal kinetic energy, or the average internal kinetic energy per particle. So substance has internal kinetic energy. And that's related to temperature. But let me ask you one question, which can be a simple question, but can actually be a hard question. If I have a liquid at 100 degrees Celsius and I have gas at 100 degrees Celsius, which has the greatest internal energy? The liquid or the gas? It?
Are they equal?
Are they equal? Why would they be equal? Why do you think they're equal?
Since they're the same temperature?
Yeah, I am kind of now. If this was the case, then they would be equal. Same temperature, same internal kinetic energy. Emily,
I use the gas because the gas has a bigger kinetic energy than the liquid
no, because kinetic energy that's decided by
temperature.
temperature, and the temperature here, well, let's assume that the liquid has the 100 degrees Celsius, and gas has
Do they have to be
100
the
degrees
same?
Celsius. But still, going from liquid at 100 degrees Celsius to a gas, I still need to supply energy to actually get it to gas. So there's another type of energy that I haven't mentioned. I just blame Anna. She should probably have mentioned it. Internal. If it's not internal kinetic energy, then it's internal potential energy. Yes. Because
The same.
here I have
In every unit.
the particles in a liquid. They're close together.
Except for ginger.
Do you agree that these particles are close together?
Yes.
And if I want to get them into a gas phase, I need to pull them apart.
Separate.
Break the bonds between the particles, and that requires energy. So, internal potential energy, that has to do with the phase the substance is in. Solid, little potential energy. Liquid, small potential energy, but still a bit bigger than for a solid. Gas, bigger internal potential energy. It has to do with the distance between the particles. So a liquid at 100 degrees Celsius and a gas at 100 degrees Celsius does not have the same internal energy. We now assume that we have the same amount of particles, and otherwise it's similar. But temperature alone does not only determine kinetic energy, not internal energy, which is the sum of kinetic and potential energy.
So the liquid has more internal energy because it has
No,
potential energy as well.
less internal kinetic energy because they have the same internal kinetic energy,
Yeah.
but gas has more internal potential energy.
Why?
Because we have increased the distance between the particles. We had to provide energy to go from here to here.
Can you explain what potential energy is? What the internal?
Yeah, but what is potential energy in gravitational potential energy, right? When the distance between me and the ground is bigger, higher the potential energy. The same with particles.
What's the formula?
If they're very close together, low internal potential energy. I increase the distance between them. How can I increase the distance between them? Yeah, by giving it energy. So energy will be stored between those two energy. So higher potential energy.
Because you're giving it energy.
Yeah, I'm giving it energy so that the distance between them increases. So gas has a higher internal potential energy than a liquid because the distance between the particles is greater, and in order to move them further apart, I have to provide energy to that substance. And that energy doesn't go away, it's being stored. Yep.
If you're going from gas to liquid, would you change the plus sign to a minus sign?
Yeah, but we're not necessarily going to do so much mathematics on it. This is just a kind of a remembering that internal energy is the sum of internal kinetic energy and internal potential energy. So we will still use a plus sign, but of course, internal potential energy could be negative if it releases energy. So that's what happens when you go from gas to liquid. It releases energy. What is the type of energy being released if the temperature remains the same?
The temperature.
Yeah. The temperature, let's say you go from gas of 100 degrees Celsius to liquid of 100 degrees Celsius, it releases energy. It's potential energy being released. So remember that. We don't just have energy due to its temperature, we have energy due to its phase. But we're not going to use formulas for it, we're just going to have to know it, how it works.
We don't have sublimation. What is that?
Yeah, that's when you go from, maybe it will be included in the chapter 10. But for now, we're not going to do that. Yeah.
Is there a reason why we're not doing calculations on it? Is it?
Yeah, I think so.
Yeah.
I think it will be. I think if you want to include calculations, well, we're going to do some calculations on it. Yeah.
Yeah.
But when we're going to model a gas, let's say, be clear, when we're going to describe a gas using mathematics, we're going to ignore the potential energy. And the reason why we do that, because I think it's extremely complicated to have formulas for the potential energy. Sometimes we just are not able to. But some calculations will be done. All right. So this was just the introduction to today's lesson. Yeah. All right. But do we accept, do you understand in terms of physics the difference between a solid, liquid, and a gas?
Yes.
And the word we kind of use to describe the phase changes. Because now we're going to get into details about what we're going to do today. All right, so the topic of today is, it doesn't take that too long, that is specific
latent heat or something like that.
Specific latent heat of fusion and vaporization. The word makes it sound harder than it is. I'm not sure what. We're not going to talk about fusion like you think in terms of fusion. Fusion just means melting here. And vaporization is going from liquid to gas. Remember that I did specific heat capacity. What was specific heat capacity?
MCAT.
Ian, what is specific heat capacity?
He takes chem, by the way.
1 week ago. And you had it in chemistry as
And he
well.
takes chem, by the way, so King's locked in right now.
Okay. Anastasia.
It's like amount of energy that we need to increase the temperature of the mass by a certain amount, by 1 degree.
Yeah.
But by 1 Kelvin.
Yeah. So,
Just
Ian,
second cunt.
specific heat capacity is the energy required to increase the temperature of 1 kilogram of that substance by 1 Kelvin. That's specific heat capacity. All right, latent heat has to do with phase of change. So latent heat or specific latent heat. I have to specific latent heat is the energy required. I'm going to look at my notes now to see that I remember the wording correctly. Require to
Thank you so much.
change the phase of a substance
This is virgin hair. Virgin hair. It's beautiful. Thank you.
Specific latent heat is the energy required to change the phase of 1 kilogram of a substance at constant temperature and pressure. And that constant temperature will be the temperature required to melt or vaporize that substance. So for water, it will be either 0 degrees Celsius for melting, or it will be 100 degrees Celsius for vaporization. So specific latent heat is basically just the energy required to either melt or vaporize 1 kilogram of a substance at one specific temperature and pressure. And the word fusion is used for melting, and the word vaporization is used for vaporization. So one example is, for instance, to melt ice. Latent heat, let's call it F here for fusion. The energy required to melt ice is actually quite a lot. Is 334,000 joules per kilogram. That's for melting ice. If you want to melt 1 kilogram of ice at constant pressure and a temperature of 0 degrees Celsius, 334,000 joules is needed to be provided. And now it's no longer ice, it's water. L for V for vaporization. I kind of just, you probably use L, you just don't really distinguish between F and it kind of comes up with the context. Actually, I don't do I remember? Should probably have read in the book, but I think it's 2,160,000 joules per kilogram. I think. It's pretty stupid if the answer is now really 2,160, but I think it's a big number. Actually, quite a lot of energy is required to vaporize 1 kilogram of water. Yeah.
So from ice to water
Yeah. At 0 degrees Celsius.
at 0 degree. Okay,
Mm.
sure, that makes sense.
That amount of energy is required.
It's a lot of joules.
It's a lot of joules, yeah.
Is that constant if we have the same mass of a different substance?
No, so this is per kilogram, right? So if we want to talk about amount of energy required in terms of a formula, if you want to find how much energy is required to melt 5 kilogram of ice, you would take that number and multiply with
Magic.
If this is the amount of energy required to melt 1 kilogram, what do you?
Five.
Yeah, 5. You take the mass. You take the mass of the substance times it with the latent heat to find how much energy is required to melt 3 kilograms or 5 kilograms of that substance. Yeah, Emily.
What's the difference between MCAT and ML?
Yeah, what's the difference between those two nice formulas that we have here? Q is equal to MC delta T. There's no cat there, but okay.
Cat.
Yeah, that's
That's cat.
That's CAT, yeah.
yeah, yeah.
Yeah.
I remember the first time the students referred to as MCAT.
What do you mean first time? Like 30 years ago. Like when is that?
I never heard it before. The first time I did the IB. Oh yeah. What is that's a very important. What is the difference between those two formulas? There's a big difference between those two formulas.
Oh, dang.
It's a huge importance to understand when to use what.
So
When are you using
CAT
that
equals
temperature?
L. CAT equals to L.
I was thinking that.
No, but they're used in two very specific cases.
But CAT equals to
Is
L.
this one like for water?
Wait.
Okay,
I thought MCAT doesn't have a constant temperature or a temperature.
Yeah, but-
temperature change.
what type of problem would you get to use this formula here? When is this formula going to be used, and when is this formula going to be used? Lamia?
Is MCAT just for specific heat capacity?
Yeah, that's related to the specific heat capacity. You want to use it when you want to find the energy required to increase the temperature of something. When you talk about increasing the temperature of something, you use the MCAT formula. And if you want to find how much energy is going to be used for changing a phase from liquid to gas or from solid to liquid, you use that formula here, the M not cat formula. Not a way to describe it. ML. And so that's something we have to practice, when to use the different formulas, because there's a lot of different formulas. Well, let's do an example, and let's do a difficult one.
No, because you had said that was your idea, and we said that could be.
So, a very practical example is what happens if I take an ice cube and put it into water.
Ice cube will slowly melt. Release
Not, but
the
not.
ice cube will gain energy from the water. Depends what
And the
temperature
water
the water
has
is at.
No,
higher
babe.
temperature.
The water literally has
Alright, so let's say I have 200 grams of
I
water
feel like in suspiciously good mood today. It's like
Right?
at 20 degrees
Takes an energy
Celsius.
When did you
from the water.
Mm-hmm.
Oh, yeah. You'll definitely cool the
I don't
water
know.
and take energy from the water.
And then we have here
no, like 6 hours.
But
Okay.
okay.
ice cube, 50 gram. It's probably a lot, but 50 gram at
So chunky
at minus 5 degrees Celsius.
Okay.
And the interesting question is, what will be the final temperature of the water? So now you're gonna use 2 minutes. Think amongst yourself what will happen to the ice. Try to be as precise as possible to describe the changes in the ice cube from the start to the end where the ice has melted and everything has reached its equilibrium temperature. Amongst the one you're sitting with, 2 minutes discussing as detailed as possible what will happen to the ice cube.
Okay. In general, firstly, it will melt. But how so, right? Bit by bit, you have to go.
Be specific. You're not being specific, you're being very
We
general.
have a ratio of 1 to 4, where is water and this is ice. So
Yeah, but it's not just gonna
water
melt.
has
Something's gonna happen before it
temperature of
melts.
20. So I'm just like thinking.
Ian, what will happen before? I agree, a phase change will happen, but that's not the first thing that will happen. Something will happen before it melts.
Ice as minus 5 degrees, where this is the ratio you have to follow.
Right? And then it. So it has more energy. Which
Yeah.
has more kinetic energy.
Water.
Water. Yeah, right. I'm like repeating what you're saying. So water. And what will happen? Will the water has a high temperature, water has a high pressure.
What will be the final temperature of the water?
It's a formula. There's like a this is
No.
it's in the book. It's my book is not here today.
How much energy required to increase?
Alright, the 2 minutes is up. Alright, so this task is not just to be creative, because what's going to come now is that if you're going to solve that question, we will have to understand what happens to the ice. So some people just say it melts. Alright. Well, actually, that may not be the case. What if the temperature? What if I put so much ice into the water that ice makes the water freeze, so that this one actually don't melt? I'm not saying it happens, but it could. All right. What happens to the ice cube? I wonder if the first thing that happens to the ice cube. What's the first thing that happens to the ice cube at minus 5 degrees Celsius added to a water of 20 degrees? What's the first thing that happens to the ice cube? Yeah, it.
What me and Faye thought is that it would reach thermal equilibrium. So then what would happen is -5 would become 15, since all the entire system would have 15 Celsius.
Well, that's not the that happens, but that's not the first. If you want to be specific. The first thing indicating there's several things happening.
So it starts increasing in temperature.
Yes, the temperature of the ice cube will increase to how much?
That's a good question. I don't know.
How much? Okay,
Zero.
so 0. Yes. First thing, for the ice to melt, it needs to increase its temperature to 0 degrees.
Then it melts.
So let's use this Q here. This is Q.
Equals my law.
That's kind of funny because it's the way you write milliliters.
Gained by the ice
A little.
cube. That's now going to be referred to Q gained. Gained.
QG.
So I'm now just going to focus on what happens to the ice cube, and that is the energy gained by the ice cube. Yeah. So the first thing that was said, that we need to increase the temperature of the ice cube by 5 degrees. So I take the mass. Okay, so what formula do you want to use here? Increasing the temperature. Is this formula here, or is this formula here?
That one up there.
Yeah.
The M.
With the cat.
With the cat.
Yeah.
With the cat.
You take the mass of the ice cube, 0.050, and you multiply by C, specific heat capacity of ice. Anyone help me? Is it a book? Is it 2,200 or is it 2,100?
Why isn't it the same as water?
Yeah, why
Or
is
am I
it
dumb?
same as water?
Yeah, no, because different types of
Nice.
kinetic energies, different types of kinetic energy, different types of motion.
Got it, got it.
Yep.
Who has
It
it?
says 2050 joules per kilogram.
Okay, then we say 2,500. No, we don't do 2,500. We do 2,100.
Girl, what is it?
Yep.
2,100? Yes.
And we
Wait.
multiply with a temperature difference of,
Could we just put the units, please? On all of them?
5 degrees.
Please.
5 degrees.
in this,
Yes.
no,
Okay.
5
please,
degrees.
5.
5.
Okay, it becomes a very messy, it is a long expression.
Okay.
Because it's kilogram
Mm-hmm.
times
What is-
joules per
Kilogram?
per Kelvin, so we kind of get, so this is in joules.
Yes.
525.
All right. So now the energy, no, now the temperature of the ice cube is 0 degree. You agree?
Yep.
Yep.
Dude. Agree?
Dude.
What happens now to the ice cube, which is now the temperature of 0 degrees? It melts.
Becomes water.
So that melts. All right. How much energy is required to make it melt? What formulas do you use?
Latent heat formula?
Yeah, latent heat formula. So I take 0.050
Mm-hmm.
times this number here. What number is that?
The latent heat.
Yeah.
Specific latent heat
Specifically.
for ice
Yeah, twice. Yeah.
fusion.
All right. So now the ice cube has melted.
Oh.
Yeah, it is correct.
That is.
What happens to the ice cube after it has melted?
The water becomes 250 grams.
So now we have water
The water, yeah.
at 0 degrees Celsius. What happens to that water? Lamia? Increase. Yeah, the temperature is going to increase. So we take now 0.050 times the specific heat capacity of ice or of water, which is
4.18.
4,100.
Oh shit.
4,200. Yeah, an increase of temperature to what temperature actually?
Oh,
Wait, should it increase by?
no, it says what temperature will increase. Which one?
We don't know. That was a concern mark. We don't really know that temperature. It's T minus
Okay.
0.
T minus 0.
Final manifestation
Yeah,
of the
yeah,
ice cube.
yeah.
Shut up.
And wait, so the first part,
Bro,
the
All
second
right,
part,
let's refresh our memory. What was this part here? What was this part?
MCAT. No.
Yeah, that's
Yeah.
what I said.
Yeah, MCAT, but yeah, so that's
The ice.
Yeah,
Ice
yeah.
and cat.
increasing temperature of ice.
Yeah.
Okay.
Makes no sense, by the way.
This is all happening to 4 ice cubes all at once.
This is ML ice.
Oh, no.
Yeah, that's melting of ice, right?
Yeah.
that is T minus 0. I just solved T minus
So the
0.
increase of temperature, the melting, and then the another
There's a
MCAT
negative. There's a negative sign.
after it's melted.
Yeah.
I'm pretty sure we're cooked. I'm
Oh, that's
That is
crazy.
wild.
That's crazy.
cold.
But
Increase to equilibrium.
but how about it? Wouldn't you combine 200 or 50 grams?
No, this is just the ice cube.
Oh.
So this is the energy provided to the ice cube. Where does this energy come from if it's an isolated system? Where does this energy come from?
The water.
The water. So the water loses energy.
A lot, I think.
So Q
QK equals.
loss.
They're equal to each other.
And they're equal to each other. But what happens to the water? What happens to the water?
It loses energy, so it like decreases in temperature.
Yeah, use MCAT formula. Times the specific heat capacity of water.
4,200.
And
Right? And it's 1.8.
how much energy does it lose? What's the temperature difference?
Yeah, it's 4.18.
20 minus 250.
20 minus T, yeah. All right.
That's it.
It's kind of like a story. This is the story I tell my kids. What happens to the ice cube?
They fall asleep before you start. So interesting.
They grow up to become physics geniuses.
All right. So if we have an isolated system, what do we do with these two expressions?
Equal each other.
Yeah, we put them equal to each other. So the thing is that
Will we ever think of doing this?
the ice doesn't cool the water. It's the water that heats the ice that makes the water
Because it has more
reduce
kinetic
temperature.
energy.
Yeah. So that just equating these two expressions, 0.05 times 2,200 times 5 plus 0.05 times 334,000 plus 0.00, no, that's too many zeros, 5 times 4,200 times t minus 0 is equal to t
I don't know.
equal to 0.200 times 4,200 20 minus t. And now I want you to practice using the equation solver to get the correct equation answer.
I got approximately
I
minus
actually have a
1.
calculator with me, that's the thing.
The day I don't.
Did you
Minus
get
0.88.8809.
Whoa, what the?
5.
What
we just combined the equations.
381.
Yo.
Okay, test. So Emily got
This
t equals to
Minus
I think it's like shifts.
0.88.
No.
Oh my god.
Is it option?
And then it minus
Yeah,
zero.
there. Calc.
okay, we're gonna practice that.
No.
All right.
Is this
Yeah,
correct?
solve
Is it
them.
minus
No,
0.4?
solve them.
All right. I just want to say that this is what you get by teacher not prepping for classes. If this is true, if the temperature is 0.9 degrees Celsius, okay, this example is wrong, then the temperature will not be, why cannot this be physically possible?
Since all the water should freeze.
Yeah, so we have ignored, then we have, now the temperature of the water will have increased, but we have neglected freezing in our formulas. So this theory works pretty well, but I put too much ice into the water, so the physics of it fails. But so if you get a negative temperature, then you have to find a way to increase nothing. But we're not going to do that. I think that will be too difficult.
I really don't know how it
But now I want you to practice solving that equation. So try to find your equation solver, write the equation into the calculator, and let's see if we can get it right. Does anyone have their calculator?
Yes.
In use currently, so.
Right.
Right. Is that slang you learned? Is that slang?
Maybe.
Maybe, yeah. Because that's what we say.
And after you've done that, you can start with question in the book 14, 15, 17, and 18.
What's the fucking answer? Why did I get positive 14?
It looks more right than this answer.
0.4?
9. I got 14.
It looks more right.
What's going
like,
on?
you know?
I got 14.7. Something.
That is wild.
Teacher, help us.
What is
Because
this?
what's
Wait, what is-
You check, okay? Think about the first one. Down to the next one. Roll. 9. Why are there 4 zeros? It needs to be 3 zeros.
It doesn't make sense to get negative values here.
This is 3 million.
No, I know what this one is. It's like 334, I guess.
Okay then.
No.
Oh.
Oh yeah.
Okay, yeah, period. Just enter it. Let's see. Good.
Right.
Exit. And then do the thingamabob. Girl, what? We're still getting 14.7. Do you like my accent?
Well, I got minus 0.4.
Yeah.
You wrote this one 2 times.
For helping me. It better do something. Negative 0.4.
I mean, it's close enough. Oh
yeah,
yeah.
But then the calculation cannot be corrected because we haven't. Then it would require ice to melt.
What?
No, ice to melt. Not water. The water
to
to freeze. Yeah.
Because 50 grams of ice is might be a lot.
Yeah.
Might be.
But the method works.
So are we doing questions now?
Yeah.
Answer is no solution.